Hello and welcome to the session 3 of discussion on machining science course. Now, while discussing the mechanism of plastic deformation in the atomic scale in the previous session, session 2, we said that for the plastic deformation to occur, there has to be a large scale slipping, where the two layers of atoms slip past each other, causing the permanent deformation, causing the two layers to stay even if the force or the stress is taken out. Now, we said also that the slip occurs in the plane or within the plane which are farthest apart from each other. Okay. That means, in between the two layers of atoms which are farthest apart from each other, because when the atoms are farthest apart from each other, in between them the resistance to plastic deformation will be minimum, and along that line, which is called the slip line or slip plane, that the plastic deformation occurs along that plane or along the slip line. Then we started discussing the amount of shear stress necessary to affect the slip. Here we said that if we had the equilibrium position or equilibrium lattice structure, and when a stress is applied with sufficient shear force, let us say, in that case the atom will be moving from the stable position to this, because of the high strain rate of deformation, and this is the distance moved by the atom as x, and this is the distance between two layers of atoms, this is b, and the atomic distance is a. So, what we said is that within the atomic distance, the stress can vary sinusoidally, and let us assume that this curve can be written as tau is equal to tau 0. Tau 0, as we said, is the maximum stress that is required for the slip to occur, or the maximum stress which is required for plastic deformation. Tau 0 sine of 2 pi x by a. So, this is the equation of this curve. This curve can be written as a sinusoidal equation 2 pi x by a, because within the a it is happening. Alright. Now, x upon a, as you understand, that this is a very small value, because this happens in less than microns, of course. So, therefore, for small values of x by a, sine of 2 pi x by a can be assumed as a 2 pi x by a, because x by a value is very small. So, therefore, we can say that the stress tau which is applied, this stress we are trying to find out, this stress is equal to tau 0 2 pi x by a, because we have assumed that sine 2 pi x by a is equal to 2 pi x by a. Alright. Now, the strain, because of this stress applied tau, which is the shear stress applied, the strain can be considered to be this movement divided by the distance between the layers, x upon b. You understand what I am talking about, that suppose if you have a material like this, a block like this, alright, and because of this stress that is you are applying, let us say this. So, the material has moved like this, it has been made like this. This movement is, let us say, x, this you must have done in your solid mechanics course, and let us say this is the distance b, this is the thickness. So, this is considered to be two layers of atoms, and here the strain, the strain is given by x upon b. Same thing we are taking here, alright, that if x is the movement of the atom and b is the distance between the two layers, it is equivalent to the thickness of this block, then the strain can be given as x upon b. Now, therefore, this tau is equal to tau 0 2 pi x by a. This can be said to be equal to this strain into the g, that is the shear modulus. This is into x upon b, which is strain. So, shear modulus into x upon b, this is equal to stress, alright, and therefore, the tau 0, which is the maximum stress that is required for the slip to occur. This can be found out by as G by 2 pi, okay, from here into A by B. As a rough approximation, let us assume that A is equal to B, roughly we say. If we assume A is equal to B, then tau 0 is equal to G by 2 pi. Now, if you see the value of G by 2 pi, okay, this is the strength of the material. So, take any material, take the strength of the material, Young's modulus, all right, and divide it by 2 pi, you will see that this is a very, very high value. Okay. And it is almost impossible to apply that much of stress, so that the permanent deformation or the plastic deformation occurs. So, then in practice, therefore, the value that the value of the maximum stress that is required for the permanent deformation, for the plastic deformation or for the material removal is much less than the value that you are theoretically getting. Why so? Let us say. Now, we are coming back to the defects or the imperfections, and we said that any polycrystalline solid, I will remind you, it actually does not come as a perfect solid, and all these polycrystalline solids normally have some kind of a defect. Either it is a vacancy or it is an interstitial impurity or substitutional impurity or something. Okay. It may be a line defect, it may be a point defect, it may be a surface defect. Okay. Now, when to the material with the imperfection or with the dislocation or with the defects, when the shear stress is applied, then instead of the bodily moving the material, the imperfections move. Okay. Now, what is imperfection? Let us try to find out. What is a defect? Defect means something that the lattice structure does not want. Okay. Now, for example, I will give you an example. Suppose a human being got sick. Okay. What does it mean? That we have temperature, we have fever, all right, because we are not well, some virus, some bacteria has gone in. Those are the foreign materials, and our organism does not want those materials or those bacteria and the virus to be in. And through the temperature, the organism is reacting in such a way that it is trying to take them out. So, normally if you see the experienced doctors say that do not take any medicine for reducing the temperature, because temperature or the fever is the natural way of organism to take out the virus or the bacteria, whatever is inside, because of what we are ill. Similar thing, that is an analogy I told you. So, similar thing happens in the lattice structure of the material. These are the defects which the material does not want to be there, and for example, in case of vacancy, the material will always try to have one atom here. So, this atom will come here, next will be vacancy here. So, this metal will come, atom will come here, and so on. Here, for example, this will be moved because this is something which the lattice structure does not want, it is a defect. For example, in case of substitutional impurity, this atom which is substituted, okay, which is substituting one atom in the original lattice structure, this atom will be pushed, all right, meaning that when this stress is applied, so these defects, whatever defect there is, this defect will be moving instead of the bodily movement of the whole lattice structure or the material. So, therefore, as we said that in practice this will be much less than the G by 2 pi, and it is actually thousands of times less than the G by 2 pi, which makes us possible to apply sufficient force which is possible to remove the material. Otherwise, what would have happened, that machine tool which is actually creating this stress, okay, the shear stress, this would have been very, very bulky and very had to be very strong. So, to apply this much of shear stress G by 2 pi. I will give you an analogy. For example, if you see, if you have noticed sometimes that on the roads where the laborers, they are laying the cables, the very fat cables of very high large diameters, and they are very heavy. So, those that cable, to pull that cable, and those cables are very lengthy if you have seen that those are the cables which are in the bobbins, okay, big wooden bobbins. So, to pull those kind of big and fat and higher diameter and heavy cables, bodily it is very difficult. So, what the laborers do, they actually make a, I will take the pen, they will make a loop kind of a thing like this, all right. And what they do is they actually push this loop, so that this loop being round, it can actually roll, okay. So, instead of frictional mu, that is the friction or coefficient of friction, it will have the rolling friction, which is much less, as you understand that. So, by either instead of moving that bodily, the whole cable, heavy cable, if you actually roll that, then it can be moved the same way, but with much less force. This is same thing what I said about the defects in the lattice structure. Or for example, you must have noticed that suppose you have to move a very heavy carpet, okay, that carpet on the floor, and if you have to move that bodily, all right, you have to apply a lot of force. For example, you have to move from this point to some point. Instead of that, if you actually make a wave, all right, and then if you move that wave, then ultimately what you see that it will be actually the whole thing will be moving, but the force which is required here to move that will be much less. So, this is an analogy, it is kind of a defect in the lattice structure, this is kind of a defect in the lattice structure, and all these defects are made so that the shear stress or the force required for creating the the deformation, okay, or the slip could be much less, all right. Okay. Next we will see the basic machining parameters, all right. In basic machining parameters, as we all know that there are 3 basic parameters in the machining. This is one is the speed, which is given in meter per minute or millimeter per second or meter per second, all right. So, this is the this relates the velocity of the cutting tool to the workpiece, all right. This is a primary motion we are talking about, meaning that when we talk about the speed, this is the cutting speed, this cutting speed relates to the primary motion. Let us give an example. You have the turning process, primary motion is the revolution per minute of the workpiece, all right. As you all know that if let us say this is the turning process for this workpiece, all right, which is fixed in the jaw chuck, all right, 3 jaw chuck, and if this diameter is d, so this rpm is the cutting speed, right, n rpm, and the cutting speed is the pi d n, this is the v cutting speed, which is in meter per minute. That is what we are talking about. That here in case of turning, the primary motion is given to the workpiece. Take for example, the drilling process. In drilling process, the drill moves, workpiece is not moving, okay, it is stationary. So, therefore, the primary motion for the drilling operation is the movement or the rotation of the drill. Here it is the rotation of the workpiece, okay. Whereas, the movement of the tool, for example, which moves, let us say in case of turning, it moves parallel to the axis of the workpiece, this is known as the feed. That means, the material is fed to the tool, so that the material can be removed. So, therefore, this is called the feed, and this is the actual primary motion. Feed, which is given in millimeter per revolution, this refers to the movement or advancement of the tool per revolution of the workpiece. As I explained it to you here, that means, in one revolution of the workpiece, how much the tool has moved, okay, in this direction. If you are giving the feed in this direction, so how much the tool has moved in this direction when the workpiece has moved one rotation. This is particularly applicable to the turning process, okay, and we will come to the milling and drilling also it is like that. In case of milling, it is little different because there are teeth. So, we will discuss it separately. Next is the depth of cut. This is the distance the tool has plunged into the surface. For example, in this case, this was the original diameter and the tool is cutting or taking this much, removing this much material. So, this is the material or this is the value of the depth of cut. All right. In other way, if we look at this in the other view, all right, suppose this is the workpiece material, workpiece, and this is the tool. All right. I am giving another view of this. So, here we have the tool and this tool is interacting with the workpiece. So, this because of that this much material has been moved. So, this is the depth of cut. Okay. And in case of drilling, in case of milling, we will show it separately and this remains, the concept remains the same, meaning that the distance the tool has plunged into the surface for all turning, milling, drilling, they are remaining the same. So, these are the basic parameters, machining parameters for all, like all machining parameter, all machining processes like turning, drilling, milling, everywhere these three machining parameters will be using. Basically, this is the speed, feed and the depth of cut. Depth of cut is given in millimeter obviously, because how much the tool has plunged into the material to remove the material. Okay. Now, let us see the chip formation, how the chip is being formed. So, I have shown you this picture, it is similar to that. Okay. This is another view and here what is shown is the cutting tool. All right. This is the cutting tool, this is the workpiece, and when the tool has plunged into the workpiece of this much distance, all right, this is the depth of cut, then the material is being removed because there is a permanent plastic deformation. So, in the tool this is the rake face, all right, this is the rake face and the rake face makes an angle with a line perpendicular to the cutting velocity vector, which is called the rake angle, that we will be discussing also in details afterwards. Now, this is the new surface which is being generated because the original surface was here, all right, and because of the removal of the depth of cut, that much the tool has plunged, the new surface has been generated. Okay. And this is the shear deformation to form the chip, and this plane is called the, or this we will call it as a plane at this moment because here it is shown as a line. So, this plane is called the shear plane and the angle between the shear plane and the cutting velocity vector will be the shear plane angle. In details we will discuss later on. So, in cutting tool, if you see the cutting tool, there are different kind of cutting tools with the different rake angles, that means the different inclination of the rake face with respect to the line perpendicular to the cutting velocity vector, and depending on that you will have the positive rake angle, zero rake angle or the negative rake angle. For example, if you see that the tool can be like this, okay, tool can be like this or the tool can be like this, right, you must have seen that, or the tool can be like this, all right. So, as we said, the rake angle is the angle between the rake face, here the rake face is here, this is the rake face, here the rake face is here, all right, and here the rake face is here. What is rake face? Rake face is the face along which the chip moves. This always you can determine, if you look at the cutting process, you will see the chip is flowing along the rake face. So, here the chip will be flowing along this surface, the chip will be flowing along this surface or the chip will be flowing along this surface. So, therefore, this is the angle between the rake face and this is the line perpendicular to the cutting velocity vector. Cutting velocity vector is here, okay, and this is the line perpendicular to the cutting velocity vector. So, this will give you an angle which we will call as a rake angle, and this rake angle is a 0, right, 0, meaning it is a straight plane. Now, here this is the line which is the line perpendicular to the cutting velocity vector again, and this is the angle which is forming with the rake face of the tool, and this angle is also rake angle, and here the rake angle is positive. This is called the positive rake angle. This rake angle is called the negative rake angle. This alpha is negative. So, For example, here you can see the negative rake angle. All these things in details also we will discuss little later. Now, the cutting action involves shear deformation of work material to form a chip. As chip is removed, the new surface is exposed. As you can see that here it is the chip is chip has been formed, and because of that the newer surface is generated. Now, if you see the picture or a sketch which is the other side of this, or if you take a cross sectional area, cross section, for example, if you see from here, if you cross it and look at this, then this will be the picture. Okay. Or if you take XX for example, that is perpendicular to this surface, the same picture it will come. All right. Now, in this picture, as you can see that this is the value which is the depth of cut. All right. And if you again take a cross section cutting edge here. So, in that case you will find a picture which is similar to that, and here you have seen that this is the rake angle. So, this rake angle is shown here. This is the between the rake face and a line perpendicular to the cutting velocity vector. This is the cutting velocity vector. Here we have it has not been shown, but this is the one which is the width of cut. This is the width. I will show you the width. This is the width. Okay. This is the width of cut. So, this width of cut can be expressed as d depth of cut divided by cos gamma s. I will show it to you what is that. Like as we said that this is the width of cut, okay, from here to here. Now, if you take this triangle, all right, this triangle will reveal this equation, that this is W, this is the W, all right. This is equal to, this is the d divided by cos of the gamma s, and the gamma s is the side cutting edge angle. Suppose if the tool is like this, okay. So, this is the side cutting edge angle, this is the angle, and this is in a particular nomenclature, we will discuss that. In different nomenclatures it is called in a different way. So, in the coordinate system particularly, going ahead I should tell you that this is called the side cutting edge angle. So, if you take the d divided by cos of gamma s, this will give you the width, and the T1 which is called the uncut thickness. The uncut thickness is given by the feed and the cos of gamma s. So, this you can find out from this very small triangle, okay, this triangle you can find out the T1 which is the uncut thickness. Uncut thickness is here, okay, this is the uncut thickness, and this is equal to feed into the cos of the gamma s which is the side cutting edge angle again. So, these things of course, we will discuss in more details in a later stage. So, now the cutting tools and the types of machining. So, this is the one which is called the typical, which is a typical lathe tool, all right. So, here we have the shank, this is called the shank, which is the portion by which the tool is clamped in the tool post, okay. And then we have the rake face, we have the principal flank face, this is the principal flank face. This edge is actually taking part in the machining. So, this is therefore called the principal cutting edge, all right, this edge, and since it is principal cutting edge, this is the auxiliary cutting edge, all right. And since this is the principal flank face, this one, so therefore, and this side, this is the auxiliary flank face, okay. And this is the mostly 4 of these parameters like rake face, principal flank face, principal cutting edge, auxiliary cutting edge, and the auxiliary flank face. These are the most important important factors or parameters in the turning tool. Let us say this is a lathe tool, typical lathe tool. Now, if we see the lathe tool, this is quite complicated because this is a 3 diagram, 3D, all right, 3 dimensional. Now, to represent or analyze the tool in the 2D, in the 2 dimensional sketch, this is easier. So, therefore, in all analysis, in most of the analysis in the book you can see, and we will also take example of the wedge shape tool. This is called the wedge shape tool. Here the basic parameters are remaining, that means we have a rake face here and we have a flank face, this is called the flank face, alright. So, in a wedge shape tool we are simplifying this, keeping the rake face and the flank face here, so that we can get the rake angle and the flank angle, and all the analysis purposes are now becomes easier, analysis become easier if we are you represent the tool, turning tool, okay, as a wedge shape tool. Now, overall the machining process can be subdivided into two basic forms. One is called the orthogonal cutting, as we know, and another is the oblique cutting, all right. Now, the basic features of the orthogonal cutting is that when the cutting edge is absolutely perpendicular to the direction of the cutting velocity vector, meaning that between this line, that is the cutting edge of the tool, and the V, there is a 90-degree angle, all right. Let me take the pen here. Okay. So, this is 90-degree, meaning that cutting edge makes an angle of 90-degree with the cutting velocity vector. So, this is the orthogonal cutting, and in case of oblique cutting the tool is inclined, as you can see, and here the angle between the cutting velocity vector and the cutting edge, this is the cutting edge, no longer remains 90-degree. This is not 90-degree. So, this is tool is inclined. Now, let us see that why these two types are. As you understand that when the tool is inclined, the material that will be grabbed by the tool, it will be gradual, okay. And it is other way around, when the tool is not inclined, when it is orthogonal cutting, the tool will be grabbing the entire material at one time, okay. You understand what I am saying, that the tool the workpiece material will be grabbed by the tool gradually, because it is inclined. So, therefore, the strength of the tool will be more, available will be more in case of the oblique cutting, and that is the reason, that is the basic reason why the oblique cutting is normally used in practice, because of the availability of the more strength, or because of the more strength of the tool. See, because we do not want the tool to be worn out faster, okay. And if the material is grabbed at a time, then there will be crumbling of workpiece material, as you understand. Tool may be broken in one part, and the life of the tool will be decreased, life of the tool will be less. So, therefore, always you can see that in majority of the cases, practical machining operations are actually the oblique cutting, where the tool is inclined with respect to the cutting velocity vector, and it is not perpendicular to the cutting edge, is not perpendicular to the cutting velocity vector. So, this is the basic phenomena or basic difference between the orthogonal cutting and the oblique cutting, all right. There are certain orthogonal cutting, very few, and one of the examples what I can see is actually like this. Like for example, if it is the workpiece material, all right, this is the workpiece, and let us say this is clamped in a 3-jaw chuck, okay. So, this is the tool which is actually moving when it is rotating. So, this is one example of the orthogonal cutting, otherwise very few examples are there. Most of the cases it is the oblique cutting in practice. So, more details we will discuss in the next session, next discussion session. Thank you very much.